Welcome back to Honors Calculus. In this video, we'll continue our discussion of continuity on an interval with an idea of differentiable functions. In fact, differentiability is a more powerful idea than continuity. A key idea I want to look at today is that if a function is differentiable, then it is also continuous, both at a point and on an interval. We'll identify a little bit what it means for a function to be differentiable and see where we can go from there. So let me get my head out of the way and let's dive in. An operator is a rule which assigns each function f to a new function, which I'll call f star for the moment. And we'll specifically look at real valued functions. That's what we're doing in this course. But if you go onward in mathematics, you'll find that an operator works more generally than that. You can assign a function of any shape or size to a different function of a different shape or size. But what I want you to think of is that an operator does to functions what a function does to variables. So our operators are letting us treat functions the way we've been treating numbers when we started looking at functions in the first place. There are a number of different operators in the world. We're going to look at two of them in this course. The first one being the differential operator. The differential operator, which we'll write as d over dx, acting on f. There's not a standard here for operators, but one common convention is that you use square brackets when you're talking about an operator acting on a function, because that allows you to still have parentheses to talk about the variable if need be. So the differential operator acting on f is the operator which takes f and maps it to its derivative, f prime. And in fact, that is something that we can do pretty generally. Here, using the limit definition, we have those two options, the limit as x approaches c or the limit as delta x approaches 0. The limit as x approaches c becomes more challenging in this regard, so we tend to use the delta x goes to 0 version of the definition here. As an example, if I have the function f of x equals 3x squared minus 5, then f prime of x is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And I can evaluate this thing at x plus delta x. This is going to be the limit as delta x goes to 0 of 3 times x plus delta x squared minus 5 minus f of x, which is 3x squared minus 5, all over delta x. When we were looking at the limit definition of the derivative before, we had a value to plug in for x here, which made the work a little bit easier. We no longer have that, so the algebra is going to be a little bit uglier, but we can still manage it. All right, x plus delta x squared is x squared plus 2x delta x plus delta x squared. Multiply all that by 3. And then we still have the minus 5. In the second grouping, be sure to distribute that subtraction. So we have minus 3x squared, and we have a minus, which is plus 5. And it's still all over delta x. Combine some like terms. We have a 3x squared and a minus 3x squared. Those things are going to cancel each other out. We have a minus 5 and a plus 5. Those things are going to cancel each other out. So what we end up with here is the limit as delta x goes to 0 of 6x delta x plus 3, not x, delta x squared, all over delta x. We can reduce by canceling out a factor of delta x in everything. We get the limit as delta x goes to 0 of 6x plus 3 delta x. All right, that's fun and exciting. From here, remember, my limit is as delta x goes to 0. My limit doesn't care about x at all. So as delta x goes to 0, this is going to give me 6x plus 3 times 0, which is just 6x. And now I have a variable expression for my derivative. Instead of needing to use the limit definition at every single point, we've taken the limit definition once in general and come up with an expression for our derivative. Let's take a look at one more example. How about g of x is 1 over x plus 1? Well then, g prime of x, which we're defining now as the derivative with respect to x of 1 over x plus 1, is the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. And it's a little bit annoying to set up, but we can manage it. The limit as delta x goes to 0 of 1 over x plus delta x plus 1 minus 1 over x plus 1 all over delta x. Clean up my notation so that looks like a plus 1 and not some sort of Japanese character. Find a common denominator between those two things in the numerator. So we're taking the limit as delta x goes to 0 of, well, I guess that'll be x plus 1 over x plus 1, x plus delta x plus 1 minus x plus delta x plus 1 over x plus 1 times x plus delta x plus 1. Oops, sorry about that. Let's get back there. I ran into my scroll bar. But anyway, that whole thing is still over delta x. And now that we have common denominators, we can add across the numerator in our fractions in the numerator of the big fraction. We're taking the limit as delta x goes to 0. Well, we have x minus x, which is 0. We have 1 minus 1, which is 0. That leaves minus delta x over x plus 1 times x plus delta x plus 1 all over delta x. And now this delta x will cancel out with that delta x. So we end up with the limit as delta x goes to 0 of -1 over x plus 1 times x plus delta x plus 1. And now that we're no longer dividing by delta x, we can plug in what happens when delta x is equal to 0. And we get -1 over x plus 1 times x plus 1, which is -1 over x plus 1, the whole thing squared. Nice, simple, straightforward, or something. But we can do it. And now that we have done it, we have a general form for this derivative. And instead of having to use the limit definition every time, if we wanted to come up with several tangent lines, we could use this formula and just plug in the value. I would like you to try the same sort of thing. H of x is x cubed minus 2x plus 5. And I would like you to find the derivative, d dx of h. Take a few minutes, see what you can figure out with that one, and I'll see you in the next video.